We're going to do a problem, a resonance, and see, imagine that you have that on a test, and it says, draw all resonance structure of the following molecule and assess them and say which one is the major contributor. So this is what I'm doing. And so the structure, the molecule that you have is the following. Now I'm going to have double bond here. So that's what the problem said, right? So we're going to say, draw all of the resonance structures and assess them and say which one is contributes more to the resonance hybrid. Right here, I need to recognize my patterns. So first, the electrons here are next to a positive charge. So those I can move. I can delocalize. Next, here, electrons. One of the lone pairs at least is going to be delocalized, and two other lone pairs are going to be localized. This one, for example, is delocalized, and I can move over here because it is allylic. So I'm just describing that the lone pair delocalized, the other two would be localized. This one right here, this lone pair is localized because it is on an sp2 orbital, which is perpendicular to the p orbitals forming the double bond. Now, this is delocalized. Having recognized my patterns, now we can draw my resonance structures. So now, first thing I'm going to do, okay, this is delocalized. I'm going to make a double bond here. And if I form a double bond here, necessarily I need to move electrons in this pi bond because I cannot expand the octet over here. And I can move that, and I will do so over here and make a double bond. When I do that, let's draw the resonance structure that results. Let's do this arrow, double-headed arrow, and then my structure. This side stays the same. The other side now will have a double bond. In here you will have a double bond to oxygen. That. Now notice again, I move those electrons over here. This is the new double bond that I'm creating. And that's I move one of the electrons to make this double bond. You still have two lone pair. Notice that in this structure, I don't have charges. So that's a good one. Remember that first octet rule. If the octet should be complete, so the structure that contributes the most will be a structure that has more octet complete for more atoms, let's say. Then the one with fewer charges. And then, of course, if there is charges, if charges are in the structure, we want to have the negative on the most electronegative atom. That's it. That summarizes the rule. Right here, this has no charges. And let's see what about the octet. In here, octet is complete. And now, here it was incomplete. Incomplete octet. Because they're going to have two bonds, one with a hydrogen, so it's 3 bonds, 6 electrons. Octet here is complete, so I am good. Complete, so all of that. Complete, complete. Again, same thing here. It's complete, and it is in nitrogen. So all of the atoms have the octet complete. So that would be a major contributor to the hybrid. Now I'm going to do something else because this is not the only resonance pattern. And to draw more, I am going to erase this part. Now we know what is localized and what is delocalized. I'm just cleaning this up a little bit and giving you more arrows to think about. But I need to erase the previous ones so not to make that too confusing, I guess. So now, let's do the pattern below. So I say here, the lone pair here is localized, so I'm not going to be able to move that anywhere. But I could move electrons here. This is delocalized, and I could move the electrons over to the positive charge. And that right there creates another structure. That doesn't look that clean. Okay. And I'm going to draw the other structure that results after doing that movement. So nitrogen here. Now I have a double bond here. Double bond. And now I have the... And we're going to analyze octet and charges to see what structure contributes the most. Here, this continues to have a lone pair. Here, there's no charges. I have moved those electrons over here. However, the nitrogen has 4 bonds, no lone pair, so formal positive charge. So these are my structures. Now, let's analyze this one and see how it contributes to the hybrid. Well, I see here that octet is complete here, so we count 2, 4, 6, 8. Octet is complete. It is complete here at the carbon. It's also complete at the oxygen. So it looks like we are good with the octet rule. Now, this, however, the next rule says that the fewer the charges, the better. This structure has positive here and negative here. So comparing the 3 structures that I have, this has octet complete everywhere, no charges. This octet is complete, but has charges. So this contribute less. And these contribute even less because octet is incomplete at that carbon. So if I have to rank them in a given numbers, I'm going to say, or letters, let's say this is structure A, structure B, and structure C. I'm going to say the most stable form, so the greater contributor is B, and that contributes more than C, and that contributes more than A. So this is assessing resonance structures.